Record. So today we're glad to have Yu to give a talk in this journal club. Yu is a PhD student in Subir's group in Harvard, and today he will talk about SYK model. Go ahead.
Okay, thanks, Shannon. Hello, everyone. I'm Yu from Harvard, working in Superior School. So today I'm going to give some introductions to the so-called Sachdev Kitaev models or SYK models. Yeah, here is the plan. So first, I want to give a very short review on the Fermi liquid theory, like how is it doing, and what thing is not good about the Fermi liquid, and why do we need a new theory? And then next I'm going to introduce the original SYK model, which actually lives in 0+1 dimension. So there's no notion of a space. There's just a time. And then as we will show that the SYK model is basically like very much like a CFT. So some of the physics can come from the CFT part of the model. But to explain some other properties, we need some corrections in the model that's actually beyond the CFT. And then after describing this 0+1 dimensional SYK model, I will talk about two other models which try to generalize the SYK model to some higher dimensions. So the first one is so-called a lattice SYK model, and then the second thing is a random teacher model, which will turn out to be very similar to the SYK models. Okay, so let's do a short review on the Fermi liquid theory. So basically, this is one of the cornerstone of a modern condensed matter theory, and it has been very successful in describing very large phases of matters. So the main concept in the Fermi liquid is given by the so-called the existence of the quasi-particle. So it is something as you might have heard in classes. It's like adiabatically connected to the free particle ground state. So therefore, the elementary excitations in the Fermi liquid are basically, you can treat it as approximately as some kind of free particles. They carry some charges, momentums, and energies, just like a free electron. But some of these properties may get renormalized. And here is a very famous cartoon that describes the distinction between a real particle and a quasi-particle. So although the quasi-particle is heavily addressed by various kinds of interactions, you can still kind of identify some of the properties that look like a free particle. And one of the famous result of the Fermi liquid theory is the following following formula for the energy of the system. So basically, Landau argued that you can expand the energy of the system in the following way. So this is the ground state energy V0, and then on top of that you get some single particle excitations that's described by this single particle energy epsilon k alpha, and then there is also a particle-particle interaction trend that's described by nk alpha and nk prime beta. And then the dynamical variables in the series are the occupation numbers of the states on the Fermi surface that's given by those nk alphas. So one thing I want to point out is that suppose our system, say a lattice, it has a size of order n, then there are exponential in n states in the whole Hilbert space. But to describe these energy eigenstates, we can only use polynomially many parameters to actually to organize the structure of the energy eigenstates. It's because here the parameters here are given by like epsilon k alpha and then f k alpha k prime beta, and then the number of these parameters will scales like a polynomial in n. Right. Okay. Okay. Here, another thing I want to add here is that the low energy, the low-lying spacing between energy eigenstates, its scales of as the order of 1 over n. That's really just because those energies here, the epsilon k alphas will scale like 1 over n. Okay, so the central concept in the Fermi liquid theory is the quasi-particle, and then one of the properties in this Fermi liquid is that the excitations will decay very slowly. So as an example, we can look at the transport, say resistivity in a Fermi liquid. So the resistivity is given by the famous famous Joule formula, and then here the thing we need to compute is the relaxation time tau here. And then, as you might have seen in classes, the relaxation time tau actually is very small. It's controlled by the phase space that's available to electron collisions. So basically, so you start from one particle, and then this one particle state can decay into two particles plus one whole, and then basically you can because of the Fermi statistics, only a very short window of energy that's at order of temperature is available for scattering, and if you actually try to estimate the phase space for particle collision, you will find that it's proportional to t squared. And basically, that conclusion leads to the fact that the resistivity of a Fermi liquid at low temperature will grow as t squared. So this is a relatively slow time scale because the natural time scale, the natural time scale we can build out of some kind of a fundamental constant is the Planckian time, which is basically like a kpt over h bar. At low temperature, this is growing actually much slower than the Planckian time scale. And as we turned out in the many kind of strongly interacting materials, the main focus here is cuprates. The Fermi liquid theory does not give the correct result. So it has been seen in cuprates that if you actually measure the resistivity as a function of temperature, it's actually linear down to like say very close to zero temperature. So the main observation in this in the measurement of cuprates is that if you try to use if you just naively use the Joule formula to understand the resistivity, you will find that the relaxation time tau is actually Planckian. So basically, the problem now is to try to just find some theory that can give you a resistivity that's linear in temperature, and then the time scale is Planckian. And that's why we need some kind of new models for this non-firm liquid physics. One of such models is so-called SYK models. It's mainly a model of a non-firm liquid systems. So there are some very peculiar assumptions in this model that might seem very, very strange. Then you might say, if you see it for the first time, you might say that it's not really reasonable to make these assumptions. So the main assumptions here is that we assume that the system is very random, and the interaction is I would say chaotic. That the interaction is a all-to-all interactions. A particle can possibly interact with any other one. So I think it's very necessary to say a few words to explain why we have these assumptions. And the first one is saying that the real system, say a cuprate, can actually be very dirty because there are real disorders and defects in a crystal. So it's not so bad to make the system random from the first place. And then the second belief is that we believe that the non-Fermi liquid physics here is actually associated with some kind of a many-body entanglement between the particles. So because the entanglement here is very robust. So it doesn't hurt to make the system random. Saying that if you make the system random, the entanglement will still be there, and we should get essentially. And the hope is we can recover essentially the same physics. And also from another point of view, there is a very powerful method of doing computations in this strongly interacting system called the dynamical mean field theory, and then the similar equations, the equations similar to SYK models will come out naturally by implementing such approximations. So the SYK model is essentially some kind of mean field theory in disguise. And then the last reason is that it's very handy to have such a random system because as we'll see, as long as you put the randomness into our system, the whole problems becomes very much solvable. And then it's also very easy to simulate it numerically. So that's why we want to put randomness. And another thing I want to mention that although I'm not going to talk in detail in this talk is the SYK model is also popular because it has many connections to the high energy physics. So it's an example of the near AdS-2 to near CFT1 duality. And then it has also some many applications in quantum chaos. So the reason is basically because their model is solvable and the people can understand many things from that. Okay. Is there any question about the introduction?
I have a question. So you mentioned in Fermi liquid, the degree of freedom is decreased to like polynomial of n. Then what about in the SYK model? Is fewer parameters or more parameters?
Yeah, in SYK models, we don't have a way to parameterize individual excitations because there are no such that many good quantum numbers. Because in Fermi liquid we have a momentum k and say spin alpha. They are good quantum numbers.
Mm-hmm.
And then they can describe the low-lying excitations. So I think in SYK model there is no and now there's no such a clear way to organize these excitations because and also because there is no quasi-particle in the system, so you don't know what you are actually labeling here.
Mm-hmm. Okay, so we have a completely different way to.
Yeah. Yeah, it's a basically a model without any quasi-particle in the system.
Okay, thank you.
Okay, so yeah, the main, okay, let me try to introduce this SYK model. So it's a so-called, what I'm going to do is the so-called the complex SYK model here. So meaning that the Fermi operators C's here are they are complex. So there's also some related models are you may see in the literature so-called the Majorana SYK model where you replace these C fermions by some Majorana fermions. And then there is also something that called a random spin chain models that we will see later in this talk. So the model looks like following. So the first term is some chemical potential term mu, and then the second term it actually describe a two-body interaction for this fermions. So the potential is given by what's called UABCD. So and then as I have advertised before, we will take to this UABCD to be drawn from some like a Gaussian random ensemble. And then it's a min is 0, but the second moment is given by U squared. And then some kind of intuitive way to think about this fixed system is that you say at the interaction process like the following. So it's like some kind of a correlated random walk or a correlated random walk of these particles. Say from the beginning, you can randomly pick two particles like this one and this one, and then you try to move them simultaneously to some other positions, like I say, move it to here and here, and then the probability amplitude of the process is also random. But you can see that because the process here is that we are trying to move the two particles together at the same time, we will naturally build a very strong entanglement between these particles. So SYK model is actually a model that has a large amount of many particle entanglement. And then also to make the model solvable, we will assume some kind of a large n limit. It's basically assume that this whole kind of mass has n different particle size, and then the couplings will scale with n in the following way. And then it actually just turns out that this whole model can be solved exactly in the large n limit. So basically, what you do here is so the first way to do it is to do some naive perturbative expansion of the model, and then you find that it can be, and then you find that it can actually resound by this so-called the Mellon diagrams. So the way is to say that the following: if you just consider the self energy here, you know that because the couplings U are random, you need to pair them up to get a non-zero result. So basically, you will need to have one U vertex here and one U vertex here, and then they are somehow paired up. And then to get a term that actually survive the large n limit, you will need three free indices in this process, and then the naive thing to draw is some Mellon like this. And then of course here the Green's function here can be further expanded like this way, and then But then, but if you use the renormalize the Green's function, you will just get some Mellon diagrams that look like that. So the bottom line here is that the larger limit of the model is given by a set of Schwinger-Dyson equations that look like following. So the first line is just the usual definition of the self-energy, and then the second line here is basically the Mellon diagram here. And also, okay, one side I want to add is that for some of you who are very familiar with working with disorder systems like these random systems, is that we usually need to introduce some kind of replicas in the system. So here we are assuming there's no replica. The reason is that so we assume we are not in the spin class phase. So the solution is replica diagonal. And therefore, it doesn't hurt to just use a simple replica. That will make things simpler in the leading large n order.
Sorry, can I ask a question? So it means that any quench disorder, you basically work the same. Is that what you mean by work with one replica?
Yeah, what means the so-called annealed disorder.
Uh-huh.
It's assuming that those yields are actually dynamical.
Mm-hmm.
So it gives the same result as the quench disorder at the leading RGN order. And I think that somebody has also looked at it at the next order. It's also the same. I think that the difference will show up at the third order in 1 over n.
Okay.
So for this talk, I will basically just I'll just be talking about the setup point physics. So it will be similar to just use the new disorders. Everything turned out to be simpler.
Mm. Okay, thank you.
So, and then another approach I want to introduce to actually deriving those setup point equations is what's so-called the G sigma action approach. So it's basically saying that we can introduce some bilocal variables. That's so-called this what we think is the Green's function as a G tau tau prime, and then it is defined as minus 1 over m sum over a c a dagger tau c a 0 c a tau c a dagger 0. And then we can enforce this definition by using a Lagrangian multiplier that we name it to be sigma. And then this sigma is later turned out it will actually be the self energy. And then you can rewrite the path integral of the problem exactly into action in terms of G and sigma. And then finally turns out that the Mellon diagram result that we have mentioned before is actually the large n saddle point of such a G sigma action. And this way it's much more convenient to work with. So it's we usually use this G sigma action. The structure of the G sigma action is that there is a determinant term here that's coming from integrating out that comes from integrating out the fermions. And then there is some sigma and G terms, and then to the force terms that actually they describe the Magellan diagram interaction. Okay, so now we can actually try. Okay, after deriving the saddle points, we can actually try to solve it. So first we want to find some like gapless gapless critical solutions. So to make the Green's function critical, we will demand that when we take the frequency to 0, the self energy should approach the chemical potential, because otherwise the system will be gapped, and then the solution will be boring. We want to find some non-trivial solution that is gapless. And therefore, in the low energy limit, it's usually trick to say that this I omega term and this mu term are actually small. They are kind of a UV. There are some kind of UV terms. It's because it's a Fourier spectrum is actually wide. It's largely high energy, but at small energy, we think that the self energy sigma is actually more dominant. So the approximation here, the so-called the conformal limit of the SYK model, is to say that we can ignore the I omega plus mu term in the self energy in the string Dyson equation. Then what we got is like a G of I omega n. It equals -1 over sigma I omega n. It's more convenient to write this thing in the time domain. It will be something like G tau 1 tau and then sigma tau 2. We integrate over tau will give you some delta functions here. And then the second equation is also written in time domain. And then by staring at these equations, you can find that there are some emergent symmetries for this set of equations. So the first one is a U1 symmetry, is that you can change the phase at tau 1 and tau 2 by some function. So the second symmetry is much more non-trivial. It's the so-called the time reparametrization symmetry. And then a simpler version to see is actually just a scaling symmetry. You can scale G's and sigmas, and the time in some non-trivial way with some scaling dimensions delta equals the scaling dimension of the Green's function is given by delta equals a quarter, and the scaling dimension of self energy I think is 1 minus delta. It's 3/4. And then you'll find that the equation here is invariant under say just a local scaling. But then for people who are familiar with CFT, we know that in 1D and 2D, the set of conformal transformations is actually much more richer than 3D and higher dimensions. So if you get a scaling symmetry in 1D, it's very possible you can promote it to a reparametrization symmetry. And the case here is true for the SYK model. So you can promote the scaling symmetry to some time reparametrization symmetry that's given by the same scaling dimensions. And then by realizing these symmetries, we find that the infrared limit of the SYK model is actually just given by CFT. So the solutions will just be a CFT.
A question here. So is SYK, so there is no notion of dimension in the SYK?
Yeah, for now there's no space, there is just a time.
But it still have some similar feature of richer conformal symmetry as 1D or 2D.
Yes. Yes, it's like the conformal group in 1D, which is the set of all the functions in 1D are conformal transformation.
Okay, thank you.
Okay, so I choose the, so usually it's people try to write conformal solutions the following way. So first, this one is in the frequency domain. So this Z is the Z is the complex frequency, and tau here is just time. So we try to write some normalization constant C here, and then the power law scaling with respect to Z is given by this Z to the 1 minus 2 delta. So such that in real domain it will be tau to the 2 delta. And then we try to write the phase of the solution, the phase of the Green's function in the following way. It's e to the minus I pi delta plus theta. And then this there is a sign of the imaginary Z term here. It's just because of the analytic properties of all Green's functions. And then in the real time, it will just given by some power laws here. So we're talking about temperature here. So the free factor for tau greater than 0 and tau smaller than 0 are different. So the parameter we have introduced here, the theta, it's some parameters we have introduced to parameterize our solutions. As we'll see later, it's actually related to the charge of the system by the following the so-called Lottinger relation. I'll talk more about that later. And we actually do more than just a zero temperature because the system has a time parameterization symmetry here. So we can try to we can do some clever mapping such that we map the whole system, which before was a straight line, into a circle at the finite t. And then by doing such a kind of mapping, we actually just write down the solution for finite temperature. So basically, what you see here is the following: the main structure of the solution is very similar to the zero temperature one. So basically, here you will just replace like tau by something like beta over pi times the sine of pi tau over beta. Okay, so here's different, and then but there is something more to do that, because we know that at the finite temperature the Green's function is a periodic or anti-periodic. So we need some way to connect the solutions that's before at the tau plus tau equals 0 plus and tau equals 0 minus together. Because when you try to map this thing to finite temperature, you will say the 0 plus and 0 minus, they're actually somewhat connected by going over the imaginary time circle. So what we're going to do here is to do a additional U1 gauge transformation for the Green's function, which is also a symmetry of the saddle point equations. So here, sorry, I didn't write this correctly. So here it's this thing is actually e to the minus epsilon times 2 pi tau over beta. And then this epsilon here is just determined such that when you go over the imaginary time circle, you can match with the t equals 0 solution. And then here is the Fourier transform. It's just given by some kind of gamma functions. Yeah, so basically this is the conformal, the so-called the conformal saddle point of the SYK model. And then by using this conformal Green's function, we can actually compute many things and infer many properties about this model. So okay, the first thing I want to the most important property here is that there is no quasi-particle in the SYK model. So there are two ways to see this. So first, you can just look at the structure of the Green's function. It's a power law. So the usual definition of quasi-particle is that there's a pole in the Green's function, but here is a power law. It's a power law, so there's no pole. So there's no quasi-particle. And the second property here is that if you can actually compute the free energy of the system by just using the set of point equations, and then knowing the free energy, you can get the entropy of the system. And actually, it turns out that the zero temperature the zero temperature limit of the entropy is actually not zero. It's actually proportional to n. So it's actually a huge amount of entropy in the system. And there is so we know the third law of thermodynamics that there at zero temperature the entropy should be a very small constant, it should not scale as n. So what's going wrong here? So the answer is that nothing is wrong. So the first reason is because the limit here is different from how we do it. So we are taking the large n limit first, and then we are taking the zero temperature limit. That means that the actual temperature of the system is actually greater to some scale, like 1 over n. So we are never truly at zero temperature. So there's nothing wrong if the entropy is non-zero. And then this non-zero entropy also it doesn't mean that there are a large amount of a degenerate ground state. It just means that the energy spacing, so for the low energy saturated, it's very small. It's much smaller than the firm liquid one. So it actually indicates that the energy spacing is it's actually exponentially small in n. So versus the firm liquid result where the energy spacing is like an order of 1 over n. So and this result also indicates that the structure of the low energy excitations are very different, because we have much more low energy states than the firm liquid theory. So that means it cannot be organized by quasi-particle structure, because the number counting isn't right. Okay. Let me comment about the charge of the system. So the parameter theta, or the one what we call epsilon, is related to theta. They are related to the charge of the system. And then there's a so-called the Lottinger relation that relates to the charge of the system to the parameter theta. So this formula can be derived in some way that's similar to the so-called Lottinger water analysis. So it's actually related to the Lottinger theorem in higher dimensions. So because the Lottinger theorem here is actually derived in the same way by using this Lottinger water analysis. So you can try to write down the definition of the charge and then in terms of Green's function, and then try to manipulate it. You will convince yourself that it can be right in this following integral. And then this the first thing here is what's called the conventional term. And then it will give you the first term in this formula. And then the second one here, it's what's called what we call anomalous. Because this term is actually equals to 0 in the Fermi liquid, because of a Lottinger water function. So basically it says that the self energy can be written as some partial derivative or some function of the Green's function g divided by g. And then by writing the things this way, you can show that this integral, this is a total derivative, and we can throw it out. But here in this Schwarzschild model, the situation is different, because this integral is IR divergent. And then if you choose and then it's very similar to the chiral anomaly in quantum field theory is that when we choose a regulator for this integral, you will get a non-zero result, and then there's no way to regulate it to make it non-zero and also preserve the symmetries. And basically, the result of this anomalous calculation is gives you the second term here. Okay, so much the properties here can just be explained by the conformal saddle point, the CFT physics. So now I will try to explain the other properties. I need to talk about the role of the UV physics in this SYK model. So let's first talk about the time reparameterization symmetry more. So we can the time reparameterization symmetry is emerging in the IR. But if you look at the solution, the symmetry is actually spontaneously broken. So the solution we get is some kind of power law. But this power law is not invariant under arbitrary reparameterizations. It's only invariant under the so-called group of a fractional linear transformations, the PSL2R group that's given by formulas like this. So the symmetry is spontaneously broken. And also the symmetry is also broken in the UV by adding this I omega n plus mu terms. So the situation here is that the symmetry is both spontaneously and explicitly broken. And then basically what it means is that the UV terms will make the symmetry positive. And then we'll see that later. And then this situation here is very similar to the so-called pseudo-Nambu Goldstone mode in particle physics. If you are familiar about that, it's the usual Goldstone mode, but the symmetry is not exact. It's approximate. So actually, to understand the role of this of the effect of these UV terms, we can do some trick to our G sigma action. So the same thing is the trick is here because we're doing some passing integral over sigma, so we can redefine the integration variables. So we'll try to shift this sigma by small sigma, which we call the UV source terms, such that we can separate the action into two parts. One is the safety part where the thing in the lock determinant just becomes sigma, and then there is a what we call UV term. It's just a sigma coupled, a small sigma coupled to Green's function, and then you can actually convince yourself that the safety action actually preserves all the IR symmetries. It's U1 gauge invariant, also time reparameterization invariant. But the UV term is not. So now we need to try to understand what's the effect of this UV term in the action. So we can actually try to employ some RG picture here. Sorry, I need to apologize for notation. This J here is the same as the U in before, because in different papers people using different notations. The J here is the same as U. Okay. To understand the effects of this UV terms, we can actually use some kind of RG picture for this problem. That's because like the IR terms are all kind of dominant in the low energy limit. That's the time scale is given by the time scale between J inverse and beta, the temperature. And also the UV terms, those are sigma terms. On the contrary, they are only large in the UV. That's at very short time scales. So basically, that means that we can replace the UV terms by some equivalent IR operators. And basically, what we do is that we can imagine like a running some kind of a RG flow for this problem, and then because as you go to lower and lower into energy scales, and then the UV operators will get decomposed into some combinations of the operators in the IR. So the conclusion we get from this kind of thinking is that the UV source current is equivalent to a linear combination of irrelevant operators in the SYK-CFT. And then the role of this UV term is to provide the energy scales for the couplings of these operators. It's such that you can write down a J. The UV source just basically provides the J term here. And then we'll just assume that it can be decomposed into a linear combination of irrelevant operators in IR. And the scaling dimensions are given by H. And I want to remark that the coefficients here, these alphas, are some dimensionless numbers. We don't know. Because if you know these numbers, you can actually solve the theory fully. But sadly, we cannot do that. We can only solve it at low energy. So basically, we just know that it's proportional to some operators. We don't know what the coefficients are. To get these coefficients, you need to solve the Schwinger-Dyson equation numerically. And a consequence of these irrelevant operators is that these operators will appear in the OPE of the C operator, and therefore the actual Green's function of the C fermions will actually be corrected by these irrelevant operators by some power loss. So this is physics that's beyond CFT. And then let me try to discuss what kind of operators are actually in the system. So we can argue that we know that there are two operators just from symmetry. There's the U1 symmetry and the Turner parameterization symmetry. From the U1 symmetry, we know that there is a charge operator Q, and because we know that the charge Q is actually just the same as related to theta. So by doing the calculation, we see that the corrections from that operator is the same thing as changing the values of theta. So we can just throw that out by using the renormalized value of theta. And then the H equals 2 operator will correspond to the Turner parameterization symmetry, which is also the energy of the system. It's also referred to as Schwarzian. That we'll talk about shortly. And then its correction is gives rise a 1 over tau correction to the Green's function. And then also there are some higher operators in the system that's given by the plots here, like 2.65, 3.77, 4.4. 58, and then the scaling dimensions of these operators, they are no universal. Like they can be determined from theta, but there's no symmetry to keep them down. So by knowing, okay, then the presence of this H equals 2 operator actually make us possible to compute the specific heat of the SYK model. So because it's a Schwarzian derivative, the second operator is actually written as a Schwarzian derivative in terms of the Turner parameterization of the Green's function. So it actually just measures how much do you cost to perform, how much action do you cost to perform a Turner parameterization operation. And it's actually the unique object that has a scaling dimension H equals 2, and it's also invariant under the symmetry, under the unbroken symmetry of the Green's function, which is PSL2R. And then by minimizing this Schwarzian action at the finite temperature, we can find that the contribution it gives to the action is proportional to temperature. And from there, you can infer the specific heat of the system is it's something like linear temperature, it's gamma T. The gamma is given by the coefficient alpha S here. And I want to point out here is that this coefficient alpha S is actually proportional to the coefficient of the correction in the Green's function alpha G. And then as a proportional, I mean that the ratio between them can be calculated analytically. Okay, and also as a side remark is that the Schwarzian is also the presence of Schwarzian term in the low energy is also related to the maximal chaos of the SYK model. That's why it is famous in the high energy community. So if you compute the so-called out of time order correlator of the model, it will saturate the chaos bound, which is 2 pi times temperature, and this is solely due to the Schwarzian term. Okay, and also the picture here about thinking that irrelevant operators is actually much powerful. It actually make us possible to predict the low energy spectrum of the SYK model very precisely. So it's basically like if you define the spectral weight of the Green's function here, and then we can by using this irrelevant operators that I've introduced before, we can actually write down the general form of the spectral weight as a series in terms of frequency. And then here we point out only the coefficients like this alphas, and then this alpha 0 and alpha 1s, they are fitting parameters, but all the other quantities here can be computed analytically. And then we can try to compare this thinking with doing numerics by exactly solving the Schrödinger equations numerically. And then what we got is that such an ansatz for the low energy structure of the spectral wave actually fits the numerical data very well. Okay, that's so much for the 0 plus 1 dimensional SYK model. So, any question about that? Okay, okay, I guess. How much time do I have?
Actually, you can go like whatever further you want, but like people can feel free to leave if they have anything after 1 p.m. Okay. The talk will be recorded, and the recording will be posted later by Seth.
I see. Okay, so after this 0 plus 1 dimensional SYK model, we can try to use this as an ingredient to construct something that actually lives in higher dimensions, and we can get some lattice SYK model that might be possible to compare with the phenomenology incorporates. So one of the early attempts is the following SYK model. It's the following thing. It's like we can view at each point of the lattice there is a one copy of SYK model that have this random interaction U. And then between the different lattice sites there can be some quadratic hopping terms that's a Tij given by this following thing. And there are different invariants about making this a T, like making T uniform or making T random, but the result turns out to be very similar. And for simplicity, I'll make T random here. And then you can do the same trick as summing those Mellon diagrams and things like that, and then you can find out that the larger n set point equation is given by this following thing, like the sub-energy has an additional T squared times G term in the action. So if you do some power counting analysis of this T squared G term, we found out it's a relevant perturbation in the to the AdS-CFT, just because it has a lower number of electrons of C operators there, so it's more relevant. And therefore, what we expect is that at the low energy, the physics will be different from the SYK model. And it turns out it's actually a Fermi liquid. And then the crossover scale here is given by the so-called coherence scale. It's given by t squared over u. So here are some numerical results by looking at this model. So here what I show is the transport data. It's either resistivity or some conductivity. So what we can see here is that very low temperature, below the coherence scale, the resistivity grows as t squared, and then at high temperatures, the slope is actually linear in t. So this is good. So we actually get a model that has linear in t resistivity, at least at elevated temperatures. But this model still has it's the first model I think to try to incorporate the AdS-CFT model into a lattice, but so it has achieved linear in t resistivity, but it has it's something that I think is not that good. It doesn't fit the recuperative phenomenology that well. So first is that the low energy is still a firm liquid, but we see in the experiment data is that it's linear T down to 0 temperature. And then also the slope of this linear resistivity actually it depends on the interaction U. So the slope here is actually not Planckian, and that means it's not the slope is not that universal as we wanted to have. And another thing is like this model has no Martinez in there, because what I mean Martinez is that the interaction between those electrons is just random, but we know that in like cuprates it's approximate to a Martin insulator, so there should be some Haber interaction terms. It's that's actually that should play some role in this model, but here we do not have it. So one of the newer model that we have been working on is the so-called the random TJ model that Subir has proposed, and yeah, and we think it could potentially describe some kind of critical behaviors in the cuprates. So what we are working with is a TJ model. So by using a TJ model, we have included the Martinez in the picture, because it's obtained by integrating out those heavy states in the Haber model, and then at the low energy we're just left with a TJ model. And then so here we have a lattice that there's hopping turn Tij's between the electrons, and then specific interactions that are given by Jij, the exchange interactions. And because we're coming out in looking at the low energy of the Haber model, we assume that the occupation number it's smaller than 1. So there is some hole doping P there. And then as a usual trick to deal with this kind of models, it's to use fractionalizations to actually solve the single Fourier constraints. And then there are actually 2 ways to do it. So what we're doing here is to fractionalize the electron C into a spin-on F and a hole-on P. And there are 2 ways to do that. You can either choose F to be a fermion, the spin-on to be a fermion, or the hole-on to be a fermion. So in this fractionalization scheme, there are 2 different ways to do it. They were called SU12 and SU21. And here mathematically it is consistent, because the group the supergroup SU12 is actually isomorphic to SU21. So at least the physical parameters, it's okay to do so. And then the physical picture of such a model is the following. The phase diagram looks like that. So at a critical point, all the 3 different energy states, like the 3 states in a single site, they have an equal energy, and then the spin correlator goes like 1 over tau, and the criticality here, as we see later, is described by the AdS-CFT model. And then on the other side of the phase diagram, you will the holons or the bosonic holons or the bosonic spin-ons will have a lower energy. So therefore, the natural thing you want to do is to condense these bosons. If I condense these bosons, you will either get a spin glass or a Fermi liquid. And then so therefore we kind of we get a candidate theory that actually describe the physics at the critical doping of a cuprate. And okay, another feature I want to mention here is that by condensing either this spin-ons or holons, you actually get a change in the carrier density. The carrier density jumps from P to 1 plus P, which is also a experimental signature that's observed in cuprate. So here is the larger phase diagram. If we also included the Haber interaction U. So basically, it's like what I have described before. It's at the U equals infinite limit on this line here. And basically, the phase transition between the spin glass phase and the Fermi liquid phase is given by some kind of SYK models. Okay, and now let me try to explain how do you make a SYK model out from that. So the previous model, the lattice SYK model, it basically just adds in this hopping term for electrons directly, okay? And because the hopping term only contains 2 electron operators, so if you just build a SYK model for these 3 electrons, the low energy limit will be Fermi liquid because it's the hopping term is more relevant. But now by actually trying to fractionalize the electron operators into some holons and spin-ons, then both the hopping terms and the spin exchange terms will become full body. Therefore, they are of the same strength in terms of power counting, so they can actually compete with each other. So some ingredients here I want to point out is that we assume that the electron operator they carries two flavors. So one is L, which is what we call the orbital here. The physical electron has 1 orbital, but here we assume that it can has many orbitals. And also the electrons can carry a spin with this alpha. It's generalized to SUN. And then in this structuralization, there are some U1 gauge symmetries about the phase of this fractionalized particles is not determined. So you need to impose some constraints for the phase charge, for the gauge charge of these particles that we set to be m over 2. And also there is a doping condition that's saying that you need to dope the system to density P. Okay, then we actually get some kind of SYK type models by assuming like a Tij random, Tij and Jij they're random constant. And then by doing this, you can also do some similar tricks as the G sigma action for the complex SYK model, and you will derive the following set of point equations for the system. So it's although it has more components, but it's actually very similar to SYK models, like the string Dyson equation has the same structure. Also, the self energy is also it's proportional to G cube. So we can solve this set of points in similar ways, and then get some kind of conformal solutions. Okay, and then one quantity I want to look at this probably as the transport. I will show you how do we get a linear resistivity from this model. So basically, you can the way to get transport is to put a system on a large dimensional beta lattice, and then on this lattice you can define a momentum on this lattice. But it turns out that the Green's function of this model that's actually depend on momentum in the larger limit. So the Green's function is the same thing as the single-sided Green's function that we have just got, and then we can just compute the resistivity using Kubo formula. And then we can now do some power counting of our Green's function. Our Green's function is also has a scaling dimension delta equals a quarter. And by doing power counting, you will find that the conformal spectral way actually scales as a constant. That means that the leading order, the conformal the conformal value of the conductivity is a constant. So therefore, we'll have to include the corrections that's beyond the CFT, those corrections from the UV terms. And then there's a very handy one at hand is that we have a time parameterization mode that has exactly each of those two. Then by including the corrections from this time parameterization mode, we'll get a 1 over tau corrections in the Green's function, and then translate this into the conductivity. We actually get a linear in T term in the conductivity, like it's the T over J. So therefore, if you assume that this term is small enough, you can just write it as rho equals rho 0 plus T times rho 1. So we get a linear interresistivity that's that actually survives down to 0 temperature, and it's also robust in the sense that it's pinned down by the time parameterization symmetry here. So the linear in T dependence is fairly robust.
The slope here also depends on the interaction, right? So it also suffers from the same problem you had before, where it's not Planckian, the scattering rate. Like you have the same problem with the slope not being universal, right?
Let me see. Okay. Okay. Maybe the slope is. No, I think if you like write these things in terms of some relaxation time, it will be Planckian. Because this whole thing has a dual picture in the gravity mode in gravity, so it has to be Planckian. The time scale has got to be Planckian.
Okay. 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 Also, another question, like a quick question. When you fractionalize the spin on the holon, when you fractionalize the electron, you're ignoring the gauge field that couples the spin on the holon, right? Or like is there?
Yeah. At the larger limit, the leading large M order, we are ignoring that.
Okay.
We're taking some stationary setup. The gauge field will settle constant.
I see. Thanks.
Okay. Yeah, that's all for my talk. So, any other questions?
Yeah, if there's no more questions, then thanks, Haoyu, for this nice talk. And next week, Peter Yu-Chen Lu will give a talk about machine learning. So yeah, I'm looking forward to it.